In this video, we'll be going over the worked example questions for topic 5.4. So first pause the video, have a try, and then we will discuss the questions. The figure shows two wires carrying equal currents into the page. State the direction of the magnetic field at point P. So the first thing we can do is use the right hand rule, because we are considering the magnetic field around wires. So by determining the direction of the current with our thumb being shown into the page as we look at it, or as we look at our hand from the back, such that we will be able to see the back of our hand, we can tell that the magnetic field will be going around in a clockwise fashion. We can draw this first. So let's actually illustrate this larger. So the first wire and the second wire. We denote the fields using the purple color. 1, and such like this. And to correct the insides, the field will look something along the lines of this. Okay, so now we've established the field around the two wires. Alright, so if we draw P at the center somewhere here, where it's equal distant from the two wires, we see that for the first wire, we'll put it as red. The influence of the field will be towards this direction, while for the second wire, we will put it as blue. The influence of this field will be along this direction. So you can see they're about the tangent of the circles which illustrate the magnetic fields. So therefore the resultant magnetic field will be the sum of the two vectors, and we'll illustrate this using orange. And we can see that the resultant magnetic field influence will be straight ahead. Therefore, the direction of the magnetic field at point P will be towards the left of the page. In this question, an electron approaches a bar magnet as shown in the figure. What is the direction of the force on the electron? What we can first do is we illustrate the bar magnet with its magnetic field lines. So let's draw the electron right here. Remember that the field lines travel from north to south. Okay. So this is a rough illustration of what the field lines look like. Then by using the left-hand rule, remember the left-hand rule, the components of it. So we have the thumb, the first finger, which is the index finger, and the second finger, which is the middle finger. The thumb denotes the motion of the particle due to the magnetic field. The first finger is the direction of the field, and the second finger shows the current. But wait, hold up. One thing tricky here is that the question says the electron approaches the bar magnet. It approaches upward like this. But because electrons have a negative charge, our current is actually headed downwards. Okay? This is our current direction. So now knowing the direction of the current and the direction of the magnetic field, we could then use the left-hand rule to find out which direction the force affects the electron. So by pointing our second finger, so the middle finger, towards us, and having the first finger, the index finger, pointing towards the left, we can then see that our thumb is pointing into the page. So here, the direction of force on the electron is into the page. And that is the answer. A tricky question. So pay attention when they ask regarding an electron. In here, the diagram shows 3 wires, X, Y, and Z. Each carry currents of equal magnitude. The directions of the currents are as shown. So for X and Z, they are into the page. So X, Z, current into page. And for Y, the current out of page. So remember the notion which we discussed in 5.4 of the arrowhead and arrow tip. So another fact that we know is that parallel currents, they attract each other, while anti-parallel currents repel each other. So we can see that X is attracted to Z, and Z is repelled by Y. But Y is closer to Z than Z is closer to X. So because Y is closer, we can see that the force it exerts is larger. Therefore, the direction of force on Z is to the right. In this question, the figure below shows a charged particle entering a region of magnetic field that is directed into the plane of the page. The path of the particle is a quarter circle. So first, justify why the charge is positive. So the first thing we can see is that the quarter circle path is towards the left side. So the force, the net force on the particle has to be towards the left. So force is towards the left. We can also see that the magnetic field is into the page due to the arrow tip indication. By using Fleming's left-hand rule, we can orient our hand such that the thumb is pointing towards the left of the page. Our index finger, which illustrates the magnetic field, is pointing into the page, which leaves our middle finger, our second hand, to point upwards. And because the middle finger represents the current, and current is the flow of charge, because of the positive charge, it's going upwards. Therefore, we can say that the charge is positive because current is going up the page. So current up the page. Part B. The particle is in fact a proton with mass 1.67 times 10 to the negative 27 kilograms and charge of 1.6 times 10 to the negative 19 coulombs. The magnetic flux density is 0.25 teslas. Calculate the radius of the proton's circular path. Alright, so we can first get the equation of the force due to the presence of the magnetic field. So we can see that this equals to force equals to the charge times the speed of the charge, the magnetic flux, and sine theta. But the sine theta term we can omit because we know that the proton is heading perpendicular or directly normal to the magnetic field. We then know that the centripetal force, or the net force needed in order to maintain a circular path, is equal to F equal to mv squared over r, the radius. We can equate these two equations together such that qvb equals to mv squared over r. So by rearranging the equation, we get the radius is equal to mv over qb. So the mass is equal to 1.67 times 10 to the negative 27 multiplied by the speed. The speed is given in part C. So 5.2 times 10 to the 6 over the charge. 1.6 times 10 to the negative 19. And the magnetic field flux density of 0.25. We then get the radius equal to 0.22 meters. About that much. Part C. The proton enters a region of magnetic field with the speed of 5.2 times 10 to the 6 meters per second. Calculate the time the proton spends in the region of the magnetic field. So the first thing we can do is to calculate how long is the path of the quarter circle. So the first thing we can do is to calculate the perimeter of the circle and divide it by 4 in order to represent a quarter. So 2 pi r over 4. And that equals to 2 pi times 0.22 over 4. So the arc length of S is equal to around 0.35 meters. We are given the speed, so we can use distance over time in order to calculate the time spent in the field. So time equals to the distance over the velocity. So 0.35 over 5.2 times 10 to the 6. And we get the time spent equal to about 6.6 times 10 to the negative 8 seconds. The last question for this topic. The figure shows the path of a charged particle. The particle goes through a thin metallic foil. We are asked to state and explain the direction of motion of the particle and the sign of its charge. So the first thing we can notice from this diagram is that the path consists of two circular arcs of different radius. The radius gets smaller, and we can think of this intuitively because the particle loses energy as it passes through the foil. So first, knowing that the foil is rolling towards the left side, we know that force is directed towards the center of the arcs. So force to center of arcs. And that the magnetic field is directed into the page due to the arrow tip illustration. So if we draw, say, a dot here to illustrate the particle, we can see that the force is towards the center of the arc. And by using Fleming's left-hand rule, by having the thumb point towards the left side of the page, our middle finger, which illustrates the magnetic flux, pointing into the page, you can then see that current is upwards or towards the top of the page. If we then follow the path that is shown in the diagram, by keeping our thumb always pointed towards the center of the arcs, we see that our hand will be rotating counterclockwise. Therefore, the direction of motion is counterclockwise. So if current is going upwards, due to what we have established using the left-hand rule, we can then see that the sign of the charge is positive. Part B. Explain why the particle exits the region of magnetic field with the same speed as the entry point. From our discussion in topic 5.4, we know that since the magnetic force is always normal to the velocity of the charge or of the particle, it follows that no work can be done to it. Therefore, the work done on the proton by the magnetic force is zero. To prove this, we know that work done is equal to W equals to F S cosine theta. So if the force with respect to the displacement of the particle is 90 degrees, so velocity is upward, but the force is acting this way, 90 degrees, we plug into cosine 90 and we get 0. Therefore, the net work done by the magnetic force is 0. So if the work done is the change in kinetic energy of the particle, with no work done means no change in kinetic energy. No delta EK. Therefore, there is no change in the speed. And that is all the answers to the questions of topic 5.4.